but I will spend extra time going through Vogelstein stuff. It's really cool, very interesting stuff, and again, I can't do it justice without the math background. But I will try, I'll kind of point you towards like papers and classes that I'd recommend you take. And a lot of the stuff, I wasn't actually there for Vogelstein's lecture, and he changed it radically this year from last year. So I'm going to be talking about stuff from my notes from previous classes or some papers I read. But if there's something that makes no sense or you didn't mention at all, please let me know. And then I'll kind of have an idea what to talk about. But at the same time, I'm going to be writing his questions as well. So I feel like what I say will have a good, will be a good predictor of what you will see on the exam, if that's what you're saying. So again, I'll hold office hours tomorrow at my regular time from 7:30 to 8:30 p.m. And of course, if you have any questions, please let me know. Yeah, no worries. It's good. Perfect. Okay. So starting with Honey's material, his stuff again deals with cognitive theory. It's a concept we've already covered a lot in this class. So this just adds to what we talked about before in terms of learning theory. In the context of this course, cognitive theory is our approach to computationally explain human behavior through functions and mathematical processes. So in what Honey presents, there are two main traditions in cognitive theory. It's the rules and symbols traditions versus the spaces and features tradition. So rules and symbols is more intuitive. It's kind of what you would expect at an introductory level when you're explaining to someone how things are processed. An example that I think is most obvious, most easy to understand is language processing. If you're trying to model how the language processing part of the brain works, you might say that there are certain neurons who process for specific words or specific symbols in language. Things that have intuitive meaning in every layer of your neural network. However, in spaces and features, it's more complex. It doesn't necessarily mean that every node or neuron has a specific meaning. We're going to talk about what spaces and features mean exactly in the later slides because that's what he focuses on in his lecture. But you can think of it this way. One is, has intuitive meaning in terms of symbols, words. Neurons maybe recognize specific words and then they activate. The other one, spaces and features approach, is saying that there are certain quantitative patterns in terms of something you can graph quantitatively, and you assign certain numerical quantitative values for the nature of a stimulus that causes the firing of an output. So that definition I just gave is kind of complex, and I'll go into specific details that will make more sense. But understand that we're going to focus on space and feature traditions in cognitive theory. Any questions about that? Yeah. Okay, so first, we've already done a lot of work with our artificial neural networks, so this is pretty simple in my opinion. Just understand some of the notation here. A represents the activation of or the activation score of a specific neuron. And so we assume that the activation of a specific neuron, in this case, it's neuron I, depends on all the inputs coming to I. So again, this means all the inputs that are going into I. In this case, we see that there are 4 inputs going into neuron I. And G is called our nonlinearity activation function. So we talked about sigmoid functions, we talked about step functions, we talked about rectified linear functions. All of these are things you should know already. And all that's saying is what happens is your input, this part equals to the sum of all the input neurons, or the activation of the input neurons times the weight between that neuron and neuron I, right? So, for example, if we say that this specific neuron is neuron J, we see that the weight between them is W or omega ij, and that rate times the activation of that specific neuron. I'm sorry, this should be a J. Tells you how much that neuron's input contributes to the overall activation of neuron I. And then this last part here is in linear algebra terms, something that is computationally easier to understand. But anytime you have a bold, it's either a vector if it's lowercase or a matrix if it's uppercase. So this is saying, and I'm going to use this for vectors, so it's very easy to understand. This is saying that, one second, let me write this out. So this is saying that the activation of all the neurons at time t plus 1. So if this is a vector, this represents, maybe 1, 2, maybe there's n neurons in layer t plus 1, or time t plus 1, right? All the neurons in this layer, their activation is based on this nonlinearity applied to the matrix multiplication between the weight matrix and the activation of all the neurons, or the vector of activations at time t or layer t. Okay? Does anyone want me to explain this in graphical terms, or like in more intuitive terms? Please raise your hand if you want me to give more of an explanation. Okay, I'll do it very quickly, because I don't think it's super important for you to understand the linear algebra, but I don't want to have this board. I shouldn't have started on that board. But basically what this is saying is, let's say that this is, like I said, neuron, etc. Let's just say there's 3 neurons in layer t plus 1. And in layer t, there's 2 neurons. So I'm going to say this is, instead of using numbers, as I did there, I'm going to use I and I. Okay, so in an artificial neural network like this, in a perceptron model, we assume that we can only go in one direction in terms of layers. You guys know this already. So we can't go from layer t plus 1 to layer t. We'll only go out this way. So let's say these are the connections, right, between the neurons in layer 1 and layer t and layer t plus 1. In these connections, again, I'm not going to write it out because I don't think it's necessary. They denote the specific connections, or the omega values, the weights between specific neurons. For example, I'll just write this one out. This is omega, and again, omega is W. I don't, just so there's no confusion. When I say omega, I mean weights. So omega I1 represents the weight between neuron I and neuron 1. Okay? So then we built a weight matrix where each row, the number of rows is the number of neurons in layer t. So there's 2 neurons in layer t, and there's 3 neurons in layer t plus 1. Right? And so then, again, I represented this as I and I, so I'm just going to do that so there's no confusion. And then each value represents the weight between this neuron in layer t and this neuron in layer t plus 1. So I1 and omega I2, omega I3, omega II1, omega II2, omega II3. Okay, so this is your weight matrix. And now we'll talk about linear algebra a little bit because he did talk about it. But when you multiply this weight matrix by the activation states of these, so activation vector at layer T is equal to the activation of AI, and then the activation of AII, like this, right? So if you multiply this, this weight with this, with this activation vector, and then you apply the nonlinearity on that matrix multiplication product, that equation right there, you end up at this result, which tells you the activation of these 3 neurons in layer T as well. So this is just a mathematical way of describing how an artificial neural network works. You take the sum, the weighted sum of the activations of neurons in layer T, and you apply a nonlinearity to get the activations in layer T plus 1. Okay, so in this concept, there's a very important thing to understand called distributed representations. And like I said before, in the state, if we were talking about the traditions before, we're talking about spaces and features. And in spaces and features tradition, each node doesn't necessarily represent a tangible concept. And rather, the stimuli and outputs represent points in a distributed space with quantitative axes. What I mean by that is these AI, AII, A12, A123 are all numbers. They're quantitative numbers. In a neuroscience sense, you may know that, or you may have learned that a neuron either fires or it doesn't. And most learning models are based like that. However, it is possible to create kind of this quantitative space where you have different combinations of this one fired and this one didn't, or both of these fired, or things like that. And you create a quantitative map of how certain stimuli and outputs are associated based on firing activity. For this class, for this exam, as you know, it's very vocab heavy. So for distributed representations, just know this definition that I've written up here, that an activation is distributed across the nodes, basically meaning that information is represented by a pattern of different firings. And a neural network, by creating these associations, allows us to create a near infinite amount of firing outcomes based on a finite number of neurons. So, in other words, what distributed representation is by having these neurons and having various firing patterns, we can create lots of different combinations that could represent different memories or different associations with stimuli. And a small variation in your stimuli. So let's say the stimuli directly inputs here. So let's say this is the stimuli, and it inputs to these 2 layers. If you vary this a little bit, you're going to have a lot of variation in the outcomes of the different spaces that I was talking about. And what that means is a variation in the stimuli that has propagated variation in the firing activity of the different layers. Any questions about that? I mean, this is just vocabulary. So if you understand what I mean in terms of distributed representations across an entire neural network, I think you'll understand what this run is. So this, I think, is better for understanding what I meant exactly by a spatial or feature space. In this case, we see that our perceptual features are basically our input features are x1 and x2. The reason why they're called perceptual is, for example, let's say this is a very simple neural network that x1 is the information you get in one eye, x2 is the information you get in the other eye, and then y1 and y2 are at the highest level of visual cortex processing. So it's a very simplified model, I'm saying. But perceptual features are the things that you perceive from your environment, right? So your eyes perceive some sort of quantitative features from the environment. And you can map that on a Cartesian graph. What this graph is showing is, you can have different values, combinations of x1 and x2. And what an artificial neural network does is it applies some weight matrix In this case, he didn't have the nonlinearity, just to be simple, but really, that y function you see up there should be like this. So really, this is what he meant, but you can also assume there's no nonlinearity. And what omega does is it maps your initial state space into your behavioral state space. So this is what I mean by state and feature models. Okay? I wish I could explain this in simple terms, and I hope you understand. But basically, all we're dealing with are quantitative combinations of firing activities that we map from one state, from one Cartesian plane to another. And so this is an example that he gives that I think is that shows a lot of concepts. So it's important to understand everything that's going on. So the first is just a perfect representation of what I was talking about. Let's say the perceptual space, we hear or we see a dog and a cat, and when we see a dog, it creates this firing pattern where x1 is like right here, and x2 is right here, right? But when we see a cat, x1 is here, so almost the same as the dog, but x2 is very different, right? So that tells you that x2 is very important for distinguishing between a dog and a cat, at least more so than x1 is. And then what our weights and our nonlinearity does is it allows us to go from this plane to this plane, where we say, for example, that everything on the right side is a meow. What we expect in terms of a sound is a meow, and everything on the left side is a bark. Obviously, that's a very oversimplification, but I'm trying to simplify the potential. And so, what this did is, based on what we saw in our perceptual state, we're able to classify an outcome in our behavioral state. And that's essentially, perfectly, in a perfect world, what an artificial neural network does. However, like I said, any variation in the stimuli will have propagated variation in your outcomes of the artificial neural network. And here, when we have noise, because in a real-life scenario, you're going to have noise for everything. So this is the difference between a deterministic and a stochastic model. In a stochastic model, or in the real world, there's noise for everything. And if you have a little variation from this perfect cat spot, we see that our results in the meow spot are kind of, they're not perfect, but they're close enough for us to say that that's a meow that we're expecting. Similar for the dog and the bark spot. So that's noise tolerance. An artificial neural network can tolerate a certain amount of noise or variation from your perfect stimuli, and still, based on how you set your classification thresholds, can still, in the behavioral space, map out pretty closely what you're looking for. Interpolation. Interpolation means, for example, we've only learned what a cat is, and we've only learned what a dog is. But what if you see something that's not exactly a cat, or not exactly a dog, or something completely different? Well, what artificial neural networks allow you to do is it allows you to see, maybe create some sort of value. It's 30% a dog and 70% a cat. And the reason why we really like feature and space or state models is they allow us to map. Okay, it's closer to a cat, so I'm going to say maybe it's going to be a meow coming up, or it's closer to a dog, so it's going to be closer to a bark. But it allows us to interpolate based on what we know to predict something about what we don't know. Okay, so that's interpolation. The opposite of extrapolation, as you probably know. Okay, so in terms of neural networks, like I said, any type of learning is just a change in weights. Changing omega, changing W is how machines learn. And there are two types of learning we absolutely need to know for this exam. Unsupervised learning is where you already know what the labeled responses are. So for example, if we go back to this, and your job was to identify, the job I gave you is if you see a dog, I want you to say bark. If you see a cat, I want you to say meow. And in order to train, like if I already told you, like this is a bark, this is a cat, this is a meow. You already know the labeled outcomes. You already know the responses. And so what you do in training is you just try to find the statistical associations between the correct stimuli and the correct output. However, in unsupervised learning, you don't know what the labeled response is. And there are a lot of examples of that. You know, what if you see a cat or a dog for the first time without any previous knowledge about what they are? Or what if you're trying to develop some machine learning classifier that is able to detect objects, or at least discriminate objects that it's never seen before? And so that's the difference in learning methods, is you need to have some sort of way to create distinctions of stimuli without knowing what the correct response or classification is. Okay? Any questions about that? So here, yeah.
So wait, so for us, if the learning is unsupervised, so do you just give it like a bunch of dog sounds and then that's it?
I think for that example, it's a little tricky. One thing I'll say is whenever you see unsupervised, think of clustering. Clustering, more so than not, is unsupervised learning. And what I mean by that is, for example, if you, well, first of all, you don't know what a bark sound is if it's unsupervised. You don't know what bark or meow are. But if I feed you a lot of stimuli, let's say I just show you a bunch of dogs, and then I show you a bunch of cats, you can create a graph. This is a form of unsupervised learning, where maybe all the dogs are here, and then all the cats are here, right? Based on just vision data alone. Well, what unsupervised learning allows you to do is you can see, here's a cluster, and here's a cluster. So from now on, whenever I see something that's closer to this mean, for example, this is called k-means clustering, versus something that's closer to this mean, I can, for example, if you get a new piece of data that's, maybe here, you're going to say that this is closer to the dog mean than it is to the cat mean, and it's more likely to be a dog. But you have no information about barks or meows, right? But that's what unsupervised learning is. It's just finding patterns in the data without knowing what the correct outcome is. Okay, so and this is, I think, a good segue from that, because the most important unsupervised learning model you need to know is associative learning, Hebb rule. I mean, you all know this very, very well, better than I do. But in our case, associative learning is any type of learning where we associate a stimulus with a particular response. We don't know necessarily, what's the correct classification, but we're able to, over time, recognize that a certain stimulus is associated with a certain response, and we bridge that, so it's called an associative link. We bridge this associative link so that in the future, if we see that stimulus, we associate it with that, that certain response. Hebb rule, as you know, is neurons that fire together, wire together, and in our case, mathematically, Hebb rule is identified by this rate change equation. It's a little confusing how he writes it, but all this is saying is that the weight between, let me write this out. Okay, so what does he say? He says that the weight between I and j in time t plus 1 is equal to the weight of I and j at time t. That's not legible, I'm sorry. Okay, the weight of ij at time t plus 1 is equal to the weight of ij at time t plus eta times ai and aj. So he doesn't say it there, but this is what he means. He means that in the next learning iteration, you update your weight so that it's equal to what your previous weight was, plus eta, And eta is the important thing here. It's the learning rate parameter. So how quickly you learn in relation to a single iteration, excuse me, times the activations of neuron I and neuron J. This is a very, very simplified version of Hebb's rule. As you probably know, a more realistic version is, what is it, like spike time-dependent plasticity, where it matters which one's postsynaptic and which one's presynaptic. But here, we're just assuming it doesn't matter, and as long as they fire together, we increase omega. If they don't fire together, this value would be negative, and omega would decrease. That's the key with this. And so, the change in omega is just this minus that, which is this part. So this part is omega, or change in omega. Cool. So that's Hebb's rule, and it's unsupervised. Yes?
How do you quantify whether or not they fire together based on the multiplication of the two?
Yeah, so let's say that if a neuron fires, A is 1. And if a neuron doesn't fire, A is 0. So, or negative 1, I think is a better. So, let me say this again. If a neuron fires, it's 1. And if a neuron doesn't fire, it's negative 1. So, in that case, what would happen is if they have different signs, if one fires and the other doesn't fire, the product would be negative, right? So then you subtract from this. But if they're the same sign, regardless of if they're both negative or both positive, the sign would be positive with this multiplication, and you would increase omega. So delta omega would increase. And so that's how you do it. Okay, so like I said, omega, so the weights are dependent on the activation correlations. That's essentially how they're determined. It's completely unsupervised because you don't know necessarily what a correct label or output is. Like I said at the bottom, there's no right or wrong in this learning because you don't know what the right answer is. For example, if you could learn that a positive sign or a plus sign in math means subtract because that's what you were trained to. That's not right, but you don't know because you don't know what the correct outcome is. But a limitation, like I said, is it doesn't discriminate between the presynaptic and postsynaptic neurons. So obviously you need some difference there because we know that has an effect on Hebb's rule. And that's essentially, here's an example that's showing that you're associating this neuron's activity with this one. That's why this vector gets bolded. And then whenever you see more information and you see this one get activated, you're going to associate it more heavily with this one. Okay, a little bit of linear algebra, dot product. Does anyone want me to go for the dot product? I hope everyone knows the dot product. For the context of this course, again, this is not really true, but for this course we can say it's true that in a feature in space tradition of cognitive theory, because we're dealing with numbers and we're dealing with points on this graph, we can kind of draw vectors, right? Let's say we draw a vector from here to dog and from the origin to cat, and the dot product of those two vectors can kind of tell us how similar those vectors are. It's not, again, it's not normalized, so don't compare it with anything else. But basically, if the dot product is greater, that means they're more similar in terms of their angle and location. Or no, it's just dependent on their angle. But as you know, the dot product of two perpendicular vectors is 0. So if they're perpendicular with each other, then that means there's no association, no similarity between them. But if they're going in opposite directions, then you still have a non-zero dot product, but it's negative. So that's, I guess, the important thing to know about this. Just know it's a similarity measure. This example that he had with battleships is, for example, the blue is your target vector, and you see these are your 3 detector, meaning like what your radar sense in terms of battleships, and the closest one is detector 1, right? And that gave you the highest outcome. That's literally it. The most similar ones will give you the highest outcome. Okay, matrix multiplication. Does anyone want me to go over matrix multiplication? Thank you. It's the dot product of the rows of A with the columns of B, if you notice. And the reason why matrix multiplication is important is because let's say you have these 3 data points. What you can do, so like I was saying before, what we were doing before is that we had our detector or our target, which I'll say is vector T, and we had the detector 1, which I'll say is this, and detector 2, and etc. And to find the similarity between the target and the director, we were just taking the dot product between these two. But now what you can do with matrix multiplication is if we have this, so instead of taking individual dot products, you can arrange your detector values as columns of a matrix, take that matrix multiplication, and this will very easily spit out for you. I realize now that these should have been rows, I'm sorry. So okay, so if you put this rows, not columns, and you do this matrix multiplication, we'll get 3 values that correspond to the similarity between T and D1, T and D2, T and D3. So matrix multiplication allows you to organize a bunch of dot products and a bunch of data much better than just doing individual dot products. I hope that's something you've learned before, whatever it is. Okay, so why do we use Heppool? When we're using our feature and space models for learning, we see that we can construct these vectors, we can take dot products, and it allows us to very quickly make these associations necessary for Heppool. Yeah, like I said, orthogonal representations have a dot product of 0, so we assume no similarity. And here, the fact that they have length 1 doesn't really matter. It's just it's called normalizing the vectors. And one way we can define the connection matrix W with linear algebra is the following, where we take the outer product of the inner product between the BART vector, and the dog vector, and between the meow vector and the cat vector. And that allows us, in a very simple linear algebra equation, to find the weight matrix without doing all individual math. Again, because you don't have to do linear algebra, I don't see how this could be tested on this exam, but I would just know that I talked about this version of Heppian learning in practice, and remember, because BART is the neuron in layer 2,